All right, welcome to The Explainer. Today we are tackling one of the most maddening mysteries of modern life, that traffic jam that just appears out of thin air.
You know the feeling, right? You're just creeping along bumper to bumper, totally convinced there's got to be a huge accident or some major construction up ahead. But then the road just opens up and there's nothing, absolutely nothing. So what in the world just happened? That right there is the phantom traffic jam.
Well, what if I told you that traffic isn't just random chaos, that it's actually a system? It's got rules. Think of it less like a jumble of cars and more like, water flowing through a pipe. And once you understand those rules, the phantom jam isn't a mystery at all. So let's decode them.
Okay, so to get our heads around this system, we've got to learn its language. And the good news is it's actually pretty simple. The entire language of traffic boils down to just three core variables.
First up, we've got something called flow. Scientists give it the letter Q. And really, it's just a head count for cars. Imagine you're standing on the side of the highway with a little clicker. The number of cars that pass you in 1 hour, that's your flow. It's basically the road's productivity.
Next up is speed, or U. This one's a no-brainer, right? It's just how fast everybody's going, on average. Super straightforward.
And last but not least, and this one is key to solving our mystery, is density, or K. This is all about how crowded the road is, how tightly packed are the cars. So, low density, you've got a wide open road. High density, yeah, you're pretty much nose to tail.
Now here's where it gets really interesting. These three things, flow, speed, and density, they aren't separate. They're all connected, locked together in this beautifully simple equation. Flow equals speed times density. You can't change one without affecting the others. This single formula, it's the foundation for pretty much all of traffic science.
So, because of that equation, every road has a breaking point, a critical tipping point. You can only push it so far before something gives. And it was a scientist named Bruce Greenshields who first really figured out how and why that happens.
Yeah, so way back in the 1930s, this engineer, Bruce Greenshields, he observed something that feels like just total common sense, right? When the road's empty, low density, you can hit the gas and drive at what he called free flow speed. But as more and more cars pile onto that same stretch of road, as that density goes up, well, everybody has to slow down. It's a fundamental trade-off.
And this trade-off creates this really fascinating consequence. It means there's a perfect sweet spot, a specific density where the road is operating at peak performance, moving the absolute maximum number of cars it can possibly handle. That's what we call maximum flow, or Qmax. It is the road's ultimate speed limit, in a way.
Okay, let's put a number on that. So for a pretty typical highway lane, where you could go 80 kilometers per hour if it were empty, that sweet spot, that maximum capacity, is right around 2,400 vehicles an hour. That's the magic number. That's the peak.
And right here, this is where our mystery really starts. So what happens when you try to cram just one more car onto that road? What happens when car number 2401 tries to merge? The whole system doesn't just get a tiny bit slower. No, it collapses. It breaks. All of a sudden, both the average speed and the total number of cars getting through, they just nosedive.
The coolest part is, we don't just have to talk about this breakdown. We can actually see it. Traffic planners have this amazing, simple graph that tells the entire story of a road.
Okay, this is called the flow density diagram. So along the bottom, you've got density, going from a totally empty road on the far left all the way to a complete standstill jam on the right. And then going up the side, that's the flow, how many cars are actually getting through. And when you plot it out, it makes this perfect upside-down U shape, a parabola.
This curve is literally everything. Watch this. As you start adding cars to an empty road, you move from left to right, and the flow goes up. You're climbing that hill. You keep climbing until you hit that very peak. That's Qmax, maximum capacity. But what happens if you add even more cars? Look, you don't stay at the top. You start sliding down the other side. And this right here reveals the weirdest, most important thing about traffic. Look at the graph. For almost any flow rate, there are two totally different ways to achieve it. You could have, say, 1,500 cars an hour zooming along at high speed with tons of space between them. That's the free flow state on the left side. Or you could have the exact same 1,500 cars per hour crawling along bumper to bumper in a dense, unstable, congested mess. That's the right side of the curve.
And that state, that unstable, congested state on the right side of the curve, that is exactly where phantom traffic jams are born. This instability,
This is the final clue. We need to solve the whole mystery.
Okay, so picture this. Traffic is flowing right at its peak. It's dense, but it's still moving smoothly. We are teetering right on the very top of that curve. And then one person taps their brakes. Just a little tap. Maybe they were changing lanes, maybe they thought they were too close to the car ahead. It doesn't matter. The person behind them sees the brake lights and has to brake just a little bit harder. And the person behind them, they have to brake even harder. You see where this is going? It's a chain reaction.
But here is the truly mind-bending part. That little pocket of slow, dense traffic you just created, it doesn't stay in one place, and it doesn't move forward with the cars. It actually starts moving backward, upstream, against the flow of traffic.
Yeah, you heard me right. This backward-moving wave of gridlock has a name. Scientists call it a shockwave. And all it is, really, is a moving boundary. It's the border separating two different traffic states, the free-flowing traffic heading into the jam and the congested traffic that's stuck inside of it.
And this right here is the answer to the whole mystery. So let's put you in the driver's seat. You're cruising along in heavy but moving traffic. Unbeknownst to you, about a minute ago, a driver 2 kilometers up the road tapped their brakes and created one of these shockwaves. Now you arrive at the back of that wave, and suddenly you have to slam on your brakes. You crawl through the jam for 5 minutes, and by the time you're out, that jam you were just in is now a kilometer behind you. The person who started it, they're miles ahead, with no idea what they caused. You look around for a reason for the slowdown, and you see nothing, because the cause is long gone.
And look, this isn't just some cool bit of trivia. This is real, practical science. Traffic planners today use what's called the Lighthill-Witham-Richards model, which is basically a souped-up version of everything we just talked about, to predict how these stop-and-go waves are going to move through the streets of huge, complex cities like Delhi.
So it turns out the phantom in the traffic jam was never a ghost. It was just math. It was the predictable ripple effect of a system pushed beyond its limit. A wave moving backward through traffic, all started by one tiny tap on the brake pedal. Which makes you wonder, right? The next time you're on a busy highway, are you just slowing down, or are you creating a wave for someone a mile behind you?